So this leads us into the idea of why sometimes, for example, copper gives up electrons to become copper 2+, and why sometimes copper 2+ takes electrons to become copper metal. In nature, we find that there are sometimes forces, and the forces will work one direction but not the other. And as an example of that, I put up there a picture of a waterfall. Water, of course, loves to go from the top to the bottom. It has high potential energy when it's at the top, like it's ready to flow, and at the bottom, of course, when you're at the bottom, low potential energy. So in the similar way, some elements will be more likely to give up electrons or to receive electrons. It kind of depends what else is around it, of course, but we're going to start talking about the forces that make it possible, and they're called electromotive force. Electrons really only spontaneously flow in one direction in a redox reaction. They'll flow from the higher to the lower potential energy. That's kind of how science works generally, but we're going to try and explore here like why some things have higher and lower potential energies and also how to predict them when they happen. So this leads us into the idea of cell potential. And when you hook up a voltmeter to a reaction, and if you look at the video here on the left, you can actually see this happening. All right, you put the leads on the pieces of metal and you get a voltage. Now right now it's 0, now it's 1.1. Take off the thing, it goes to 0, put it on, it's 1.1. Cell potential, which is measured in volts, all right? For example, like this volt right here, that's actually a way to measure the potential of a cell. And we're going to see that there's ways to figure out what every half reaction has. If you put zinc into zinc 2+ solution and copper in copper 2+ ions, you're going to see that the cell potential is 1.10 volts, and electrons flow from the zinc to the copper side. So zinc makes zinc 2+, and copper 2+ ions make copper. EMF, the electromotive force, is a way to measure how electrons are driven, all right? It's all about the energies they have. And if you know how to work EMF and cell potential, you can figure out cell directions for things, lots of things, which is pretty cool. If you connect that zinc and copper cell that we've been looking at, the voltage is 1.10 volts at 25 degrees Celsius, and when the concentration of the ions are 1.0 moles per liter. So notice this right away. There's a temperature and there's also solution concentrations, and we'll talk in a little bit about how those change if you change those values. But for right now, 25 degrees Celsius, 1 mole per liter, that kind of stuff are standard conditions. That's what we're talking about. The standard cell potential is the cell potential under these standard conditions. 25 degrees Celsius, 1 mole per liter concentration. If you have a gas, it would be 1 atmosphere, and it's something measured in volts. E, capital E, is the symbol for cell potential, and it's measured in volts, V. If it has a little 0 by that, that means that it's standard conditions. So for this reaction, under standard conditions, the cell potential is 1.10 volts. And we'll see what to do with that here in a little bit. If you looked at your own batteries, batteries have a voltage on them as well. And you bet that voltage is related to the voltages we're going to talk about here. We'll talk a little bit about that towards the end of this chapter. The zinc to copper reaction that we've been looking at has 2 half reactions, zinc going to zinc 2+ and copper 2+ going to copper metal. And if we knew the half cell reactions potential, we could then add them together to get the overall cell potential. Like we know the overall cell potential is 1.10 volts, but what are the half cell reaction values for zinc going to zinc 2+ and copper 2+ going to copper? So scientists need like a ruler stick, a way to measure cell potentials for reactions. If we had that kind of system, then we could measure half reactions to give overall reactions, blah, blah, blah. So this slide is introducing the measuring stick, if you will, that scientists use to measure cell potential. And the measuring stick that's used by electrochemists is called the standard hydrogen cell. And that's sometimes a tongue twister. The standard hydrogen cell is also known as SHE. SHE stands for standard hydrogen electrode, all right? And this is a half reaction that electrochemists have all together coming in on and agreed that this should be like a ruler. Now, if you think about it, to measure length, everybody had to get together at some point in the past and decide that, yes, this length is a meter, okay? So the meter stick is arguably the way that people measure length now. It's actually different, but we'll say it is. The standard hydrogen electrode is equivalent to the meter stick. It's a way that scientists can measure the cell potential in volts for half reactions. This reaction right here, which is 2H plus, which is an acid, aqueous at 1 mole per liter, combines with 2 electrons to make hydrogen gas at 1 atmosphere of pressure. This is the standard hydrogen cell, the SHE electrode, okay? And it's decided upon by electrochemists everywhere that the cell potential will be 0.00 volts. Now, that may seem an unusual measuring stick to use, but we're going to see that cell potentials can be both positive or negative. And the way that this one's written, 0 volts, it's like good to go in either direction. So there is a method to the madness. It seems strange at first, but for right now, just realize that standard hydrogen electrode is just acid, plus some electrons, making hydrogen gas. And it is a double-headed arrow. It's a two-sided street. So you can go from acid to hydrogen gas or hydrogen gas to acid, same cell potential. Let's go to this reaction. This is a battery. It's zinc and zinc 2 plus, and we also have the SHE electrode on the other side. And we know that because there's H plus and H2. Now, notice that the electrons are flowing from the negative side to the positive side. So they're flowing this way. That's going to be important to us. The zinc is the negative electrode. It's where the electrons are coming from. So that means here that zinc is being oxidized to zinc 2 plus. This left-hand side here is the anode. And if that's the anode, then by default, the other side is the cathode. So that side is gaining the electrons, 2H plus 2 electrons going to H2 gas. That's the cathode. So in this reaction, zinc is giving up electrons to make zinc 2 plus, and H plus is gaining electrons to make H2. And when they measure the cell potential here, which is totally doable, you head up one of those voltmeters and stuff, it's pretty easy in physics, you get a positive 0.76 volt value. Well, if we know that the overall cell is 0.76 volts, and we know that the SHE electrode is 0 volts, it's not going to be too hard here to calculate the cell potential of the zinc going to zinc 2 plus. We don't know what that value is. Zinc going to zinc 2 plus is a mystery. But we know that SHE electrode is 0, and we know the overall cell potential, positive 0.76 volts. Well, notice here that if you literally combine the reduction and the oxidation parts, you get this one. You can also literally combine E zinc plus EH plus to give E net. It's literally that simple. And E zinc is an unknown. Let's call it X or whatever. We don't know what that is, but 0.76 minus EH plus or 0.76 minus 0, that's going to equal Z zinc. E zinc, positive 0.76 volts. So this is a way that we can, as scientists, figure out the cell potentials of these half reactions. And we just figured out that this reaction right here, zinc going to zinc 2 plus 2 electrons, it's 0.76 volts. Pretty cool. This is the first one of the half potentials or cell potentials for the half reactions that we figured out. We figured it out using the SHE electrode, our measuring stick, if you will. We hooked all of this up and found the overall cell potential was positive 0.76 volts. So knowing that, we've got now the half potential for the zinc going to zinc 2 plus reaction. Zinc is a better reducing agent than hydrogen. Now remember, reducing agent means oxidized, and zinc here wanted to be oxidized. Hydrogen didn't want to be oxidized as much as zinc wanted to be oxidized, and that's what we found when we set this stuff up. So you can use this then as a way to calibrate if something is better or worse than another thing. And zinc here wanted to be oxidized. Hydrogen gas did not want to be oxidized. It wanted H plus to turn into hydrogen gas. So zinc is a better reducing agent than hydrogen. Zinc is easier to oxidize than hydrogen. Let's do the same thing now, but now we're going to do it with a copper reaction, okay? And this has copper and copper 2+, and on the right side again is the She electrode. But notice here the signs, all right? First of all, the signs are different. We've got a negative on the right and a positive on the left. So that means electrons are flowing this way. And also notice the cell potential. It's a different value. It's only positive 0.34 volts. So a lot of differences here in this copper versus She electrode reaction. Now in this case, the She electrode is the supplier of electrodes. It's the electrons. It's the anode. It's the site of oxidation. Hydrogen here wants to go to H plus and electrons. Electrons are going from the She electrode to the copper side. And if they're going to the copper side, that means that the copper is the site of reduction. Copper 2+ is gaining electrons to become copper metal. So the reduction here is on the copper side. Oxidation is on the She side. So you're seeing here that the metals, zinc versus copper, they're doing different things, all right? With the She electrode, the zinc was giving up electrons, but with the She electrode, the copper is gaining the electrons. A different kind of system here. So like before, we're going to figure out the half cell reaction for copper 2+ going to copper. And like before, the measured cell potential of the whole thing, positive 0.34 volts. Well, this comes from the fact that copper 2+ going to copper is 0.34, because copper going to copper 2+ plus She, 0.34 plus 0 is 0.34. Big surprise, copper 2+ going to copper, positive 0.34 volts. Now notice the copper here is being listed as a reduction, copper 2+ going to copper. In the zinc reaction, zinc going to zinc 2+ plus 2 electrons had that other value. So zinc was best written, if you will, as an oxidation. Copper is best written as a reduction. Now let's put them both together. All right, and this is what we did originally. All right, we're going to have zinc at the anode. It's going to be creating the electrons for the copper, which is accepting them. So the anode is the zinc side, the cathode is the copper side, salt bridge, etc., etc. Now, this is where it gets kind of fun. Zinc here is going to zinc 2+ plus 2 electrons, and the cell potential positive 0.76 volts. The copper 2+ is accepting those electrons, make copper metal, and we saw that its cell potential positive 0.34 volts. Well, if you add up the two half reactions, you add up the two cell potentials, 0.76 plus 0.34, bam, 1.10 volts, and that's what was measured when we saw originally in this problem a long time ago. So this is how people find the cell potentials for all these different half reactions. In the ideal world, they'd use the She electrode, all right, and they'd compare it to She and figure it out. However, to be honest, using strong acids and hydrogen gas can be kind of weird. So instead of using She, sometimes people then would use the zinc reaction or the copper reaction, and they can compare the overall cell potential to the cell potential of the half reaction in order to find the missing half reaction. So it's kind of cool how they develop these kind of tables. In this problem, we want to determine the cell potential for this reaction, and it's nickel plus the mercury 2+ ion going to nickel 2+ and 2 mercuries, all right? If the reactions are already written in the correct form, you can literally just add up the half cell reactions, the 0.25 volts and the 0.79 volts, to give the overall cell potential. So if you look at these half reactions, well, nickel is a reactant and nickel 2+ is a product, so that looks okay. Mercury 2+ is a reactant. Yep, that's okay. And mercury is a product. That's okay. The electrons will cancel if you add them. So literally in this problem, it is as simple as adding up the two half-cell reactions. So 0.25 plus 0.79, that comes out to be 1.04 volts. That's the cell potential of this reaction. So notice that if everything's set up right, you literally add the half reactions together and you add the cell potentials together to give the overall cell potential for the whole reaction. The 1.04 volts is what you would measure if you put nickel and the mercury 2+ ions together in a voltaic cell.